Namaste dear students, I am B.G.Shinde sir and we are discussing chapter number 3 Kinetic Theory of Gases and Radiations of 12th Standard Physics. Today we see lecture number 2 and today's topic is expression for pressure of ideal gas. You listen this lecture up to end and also subscribe YouTube channel and tell your friends about our lectures and tell them to subscribe. So let us consider a cubical box. This is a cubical box. Length of each side of this cubical box is capital L, and suppose that we have drawn x-axis along one edge, y-axis along its adjacent edge, and z-axis in this direction, which is starting from one corner of the cube. So draw x, y and z axis which are starting from the common point, which is one corner of the cube. Then this cubical box contains the gas, which is ideal gas, which has n number of molecules and mass of each molecule is m, small m, and volume of the gas will be L cube. Now there is one property of the gas we have seen in 11th standard. There is one assumption that all the gas molecules are in state of the random motion. Also, they collide with each other. Also, they collide with the walls of the container. So we use this property, but we neglect the collision between the molecules. We neglect the collision between the molecules. We consider only the collision of the molecules with the walls of the container. There are 6 walls, 6 sides to this container, and all the molecules will collide with the walls of the container to these 6 sides. So, let us consider one molecule. Consider one molecule of mass m which is traveling along x-axis with velocity v. If v is velocity of the molecule and it is moving along x-axis, so we consider the component vx which is along x-axis. Actually there are 3 components, vx, vy and vz, and since this molecule is moving along x-axis, we consider velocity of the molecule along x-axis as vx. This is first molecule. Then this molecule collide with this shaded area. This molecule collide with this shaded side of the cube. There are 6 sides, and we have considered this shaded side parallel to yz plane, and this molecule will collide on this surface, and before collision its momentum will be m into vx, and after collision its velocity will be minus vx. Means the velocity will reverse, magnitude will be same, and after collision its momentum will be minus m into vx, and therefore change in momentum delta px will be equal to minus m into vx minus m into vx, and so change in momentum will be minus twice m into vx. So change in momentum of the gas molecule when it collide with the surface will be minus twice m into vx. Now this negative sign indicates that the gas molecule gives momentum to the surface. It gives momentum to that area. So it gives momentum to the area, and therefore change in momentum of the surface will be plus twice m into vx. Means this momentum is given to this wall of the container, and therefore the momentum of the wall of the container will be plus twice m vx, which is the change in momentum of the surface or change in momentum of the shaded area. Then rate of change of momentum is denoted by delta px upon delta t. Rate of change of momentum will be given by delta px upon delta t. Let us find this rate of change of momentum. So first we determine what is delta t. Delta t is the time between two successive collisions of the gas molecule with the same surface. This is the surface which is shown by the shaded area. This gas molecule collide with the surface, it will rebound. After rebound, it will travel distance L. This distance L. Again, it will rebound from this surface and it will collide with the same surface. So what will be distance travel? This distance is L, and again it will come to the same surface, and so total distance traveled by the gas molecule will be twice L. So distance traveled by the gas molecule divided by the velocity of the gas molecule, it is Vx. So the time between two successive collisions is equal to distance traveled by the gas molecule divided by the velocity of the gas molecule. Now let us put this value of delta t and value of delta px in this equation. So delta px upon delta t is equal to twice mvx upon twice l upon vx. Now this 2 will be cancelled, and so this is mvx square upon l, and this is rate of change of momentum. This is rate of change of momentum of the surface due to first molecule. And so we write here, this is for the first molecule, and so we write here delta px1 upon delta t is equal to mvx1 square upon l. This is for first molecule. Now similarly for second molecule, you can follow the same procedure, but similarly you can write for second molecule it is mvx2 square upon l. For third molecule it is mvx3 square upon l, and similarly for last molecule it is mvxn square upon l. We have taken n molecules and therefore we have written this mvxn square upon l. So these are the rate of change of momentum of the surface S due to each molecule, due to all molecules. Now, because of the rate of change of momentum, the force is exerted on this surface by Newton's second law. So, the average force which is exerted on the surface will be F is equal to the change in momentum due to first molecule plus change in momentum due to second molecule plus addition of all these. So it is mvx1 square upon l plus mvx2 square upon l and plus mvxn square upon l. So this is force F is equal to m upon l in bracket vx1 square plus vx2 square dash dash. So we can write all the velocities here. So this is the average force. This is the average force. Say this is equation 1. Now we know that velocity, average velocity Vx, average square velocity is equal to Vx1 square plus Vx2 square plus Vxn square divided by n. This is called a average square velocity. It is also called a mean square velocity. So average square velocity Vx square is equal to this, and therefore n Vx square average. This symbol denotes average. This is not vector, but this is average, and so this is Vx1 square plus Vx2 square dash Vxn square. Now put this value of Vx1 square plus Vx2 square in equation 1. So we get force F is equal to m into n Vx square average, and it is divided by L. So this is equation number 2. This is the force. Now what is pressure? Pressure is equal to average pressure is equal to average force divided by area. What is this area? Area of this shaded portion. The area of this side, and it is denoted by capital A. So this is equal to, now put value of F, n Vx square bar divided by L into A. This is pressure, and say this is equation number 3. This is the formula of the pressure. Say this is equation number 3. Now here what is N into A? Length multiplied by area. This is area A and this is length L, and this represents the volume. And so we can write mn Vx square bar divided by V, and this is the pressure, equation number 4. This is average pressure. Now we know that velocity of the gas molecule V is equal to Vx square plus Vy square plus Vz square. Means velocity of the gas molecule has 3 components. So square of the average is equal to Vx square bar plus Vy square bar plus Vz square bar. The velocity of the gas molecule is given by Vx square plus Vy square plus Vz square, and this bar indicate, this line indicate the average velocity. So this is velocity. Now also it is found in figure that Vx is equal to Vy equal to Vz. Means all the velocities are same because of the symmetry of the figure, and also gas molecules of the same size. And so we can write V square bar is equal to 3Vx square bar, and therefore Vx square bar is equal to V square bar upon 3. Means we get Vx square bar is equal to V square bar upon 3. Now let us put this value in equation 4. So average pressure will be equal to Mn into V square bar. It is divided by 3 and into V. This V is a volume and this V is a velocity. So there is a difference in this symbols. On numerator it is a velocity and on denominator it is a volume. So this is velocity, and this is expression for average pressure. This is expression for average pressure of the ideal gas. So you take all the notes, you write all the points on the board. Also, if you want, you can take the screenshots, and by using screenshots you can write all the notes, all the expression. This is one of the important expressions, and that's all for today's lecture. Thank you very much.